You're listening to Let's Talk Creation with Todd Wood and Paul Garner, the creation show where we learn, grow, and worship.
Well, welcome back to another episode of Let's Talk Creation with Paul Garner and Todd Wood. I'm Paul Garner.
And I'm Todd Wood.
Just remember, as always, to hit that subscribe button and the notification bell so that you get to hear about all of our new content. Do share the podcast with your friends. Leave us a positive review, like our episodes, all of that stuff. That really helps us to spread the word about the podcast. It's good to see you all again for another episode. And today we've got an interesting topic. Today, Todd, we are going to be talking all about the geology of oil formation. Oil is of enormous importance, of course, to the world economy. It provides fuel for transportation, provides oils for heating and lubrication, lots of other sort of industrial applications, a whole host of petrochemicals and so on. And of course, the nations that have very large oil reserves are among some of the wealthiest nations in the world. So it's really important sort of economically. But oil has also played a very significant role in the creation-evolution debate over the years. So critics of creationism have often sort of said the young Earth model doesn't provide enough time for the formation of oil. And there are also critics out there who say that if you're a young Earth geologist, you just wouldn't be able to locate economically viable deposits of oil because they rely on kind of evolutionary techniques to find oil. So these are the kinds of things that are kind of floating around sort of in the ether as kind of criticisms of young age creationism. And as we're a creationist podcast, I thought we should invite someone who knows about these things to talk about it and ask whether these are valid criticisms of the young Earth model. And so to help us answer these questions today, we've got a very special guest, Richard Bruce. Welcome, Richard. It's great to have you with us.
Thank you very much, Paul.
Now, Richard is a geologist. He has over 40 years experience as a professional geologist, mostly in oil exploration. So Richard is just the guy to help us answer some of these questions that we're thinking about today. So we're very grateful to have you with us, Richard. Why don't you begin just by telling us a bit about where you're based and about your professional background, because I'm sure that already some of our listeners have detected that you do not have an American or a British accent. So tell us about that.
Oh, really? Yeah, I'm an Aussie. I'm from Western Australia. The West is best. Yeah.
Yeah. So tell us about your life as a geologist, Richard. You've had a long career in geology, and you've worked in industry. You've worked for government, I think. So just tell us some of the things that you've done in your career.
Yeah, industry, university, and government institutions. In industry, earlier in my career, I worked at drilling sites in a variety of environments. Oh, by the way, I thank God for His wonderful grace for all the adventures I've had in life, as a geologist. But so I've worked in Pakistan and Australian deserts, Borneo jungle, Philippines rice fields, and the UK North Sea, and many other places. At university, I initiated a Petroleum Exploration Society of Australia journal article. It was chosen as the front cover and lead article. I was stunned. I didn't think it would get published. The conclusion was that rapid petroleum generation may be more widespread than commonly believed. That's a secular article. In government, I promoted bid rounds. That's where companies apply to get acreage so they can explore, apply to government. So I promoted bid rounds, got big packages of information for them to consider areas. So the prospectivity of the area, all sorts of information, and promoted them at conferences in Australia, around Asia, North America, and the UK. Now, I commenced writing young Earth creation articles using the pseudonym Harry Dickens. The reason for that is that I'm writing these in a private capacity, not as a representative of my secular employer, rather.
Yeah. So some of our listeners, if they follow the creation literature, may have read those articles by Harry Dickens, but those articles were written by you. And some of them I know were on the topic that we're going to be thinking about today, about oil generation, oil exploration, and so on. I've got lots and lots of questions about all of this. And I guess we should start with some sort of basics. So first of all, what is oil? I mean, how does it form? Where does it come from? Just sort of fill us in on some of those details.
Okay, petroleum or crude oil is a naturally occurring fossil fuel. It's composed primarily of hydrocarbons. And where does it come from? Well, the source is mainly algae and plants that have been buried under layers of sediment and transformed by heat and pressure. The heat can come from greater burial depth and from flowing subsurface hot water. Algae is a good source for oil. Land plants are a good source for coal and natural gas.
Okay, so it comes from basically algae and plants. So this is why we call it a fossil fuel, because it has an organic origin.
That's correct.
Now, I have heard about some people who sort of claim that oil, or at least some oil, has an inorganic origin. I think, wasn't there a geologist called Thomas Gold who was sort of well known for this perspective? What do you think about that? Is most of the oil organic? Is some inorganic?
Well, the inorganic theory of petroleum formation is that hydrocarbons are generated from non-biological sources, such as methane within the Earth's mantle and migrating upwards into crustal reservoirs. However, researchers have been unable to cite any commercial occurrences of abiotic petroleum.
Right. So all of the oil that we have, you think, is organic? There's no inorganic.
I mean, there might
petroleum
be
at all.
some, tiny, less than 1% type situation, but essentially it's organic.
Yeah. And can we tell that from the chemistry of the oil? I mean, how do we deduce that?
Yeah, the oils have got chemical markers which indicate origin from plants and algae. So there's specific kind of organic chemicals that sort of give the game away.
Yeah. Now, in the introduction there, when we sort of opened the episode, I mentioned the way that critics of creationism have often sort of appealed to oil as a potential challenge to the young Earth model. I'm sure you've come across that yourself. So, I mean, just tell us, how do they see this? What is the perceived problem in terms of oil formation for the young Earth viewpoint?
Well, I don't see a problem, but anyway, but it's just that geoscientists are commonly trained within an assumed deep time framework. We've only measured radiometric dates in less than 200 years, and they're extrapolating that to hundreds of millions of years. It's an assumption. It's not not observable. However, world-renowned petroleum geochemist Tiso and Welt, they wrote a textbook, Petroleum Formation and Occurrence. They say in their textbook, temperature is the most sensitive parameter in hydrocarbon formation, not time. So you crank up the temperature and the rates of reactions go exponentially greater.
Mm-hmm.
So time is not the most important factor. A real-world example is in Russia, in the Moscow Basin. There's Carboniferous brown coal. It's buried at less than 200 meters, but it's never matured to black coal, despite supposedly being over 300 million years old. So it's not time at all. It's temperature.
Yeah. So the idea is that organic material, algae, plants are buried in sediments, and then what actually happens to kind of turn those materials into oil? How do they degrade?
Well, it becomes something called kerogen. It's just sort of like the decaying of the algae in plants. It becomes something called kerogen, which is a very fine grained organic material. And as that is heated further, that's when it cracks down into oil and gas.
Right.
So
yeah, and temperature is the main factor rather than time. So
yeah,
time's not the hero of the plot.
Yeah, pressure would have an effect as well, but it's principally temperature.
Yeah. And in terms, so the elevated temperatures that you need to produce the oil, what geologically would generate those elevated temperatures?
Well, just the deeper, when organic material is buried, the deeper you go in the earth, the hotter it gets, because you've got heat coming out from the mantle. There's a thing called a geothermal gradient. So just the burial itself and the weight of overlying sediment as well is a factor. So but there's also other things. This petroleum article that got the front cover, we came up with another idea, that there's moving hot water in the ground because you've got permeable sediments, and where the water is heated up at depth, it can also migrate to a source rock and heat up the source rock to produce oil and gas. We looked at a number of case studies for that, a number of basins around the world. San Juan Basin in the US, Cooper Eromanga in Australia and other places where there is that other effect of moving hot water.
Yeah. And this hot water, this hydrothermal water, could it be related to the intrusion of sort of igneous bodies, where you have sort of hot plutons being intruded? They're presumably, you're setting up a kind of convection cell where you're having circulating hot water. Could that be a factor in producing oil?
It definitely is. In fact, after my petroleum paper was published, I was invited to speak at an international conference on coal seam gas and oil in Brisbane. The University of Queensland invited me to speak there. They had question time. They chimed in to support the ideas I'd presented. They said that there was evidence in the Bowen Basin, where there's coal in Queensland, that there was, from isotopes and from coal macerables, there was this effect of hot water coming off of intrusions, So it was just really reinforced,
Yeah. Are there any places where we can actually see oil being generated today? Did it all happen in the past, or is there still activity today that's producing petroleum?
Well, the Gippsland Basin in Bass Strait, offshore Victoria, oil is still being generated there, but there are other quite radical places where extremes of temperature in the seabed, like the Gulf of California and the Red Sea, you've got a hydrothermal fluid coming out of the seabed. It's encountering organic rich mud, and it's forming oil and gas like instantaneous. But that's 300 degrees Celsius. A colleague of mine, Mike Middleton, Dr. Middleton, he did all sorts of modelling, and he believed that even at 200 degrees, you could get the formation of peak formation in 1,000 years.
Hmm.
But so it's temperature. It's not time.
Mm-hmm. That's amazing that we're actually seeing almost instantaneous oil formation even in the present day in some of these locations. That's kind of a mind-blowing idea. One of the other things I have sometimes wondered about is what experiments people have done in the lab. If people tried to replicate oil formation to sort of study what are the various sort of factors involved.
Yeah, like in Australia, like CSIRO have done experiments to try and simulate what it would be like in the subsurface. And petroleum can be generated in a period of even a few years or less at appropriately high temperatures and in the presence of water.
Mm.
That was their sort of conclusions.
Mm. Yeah, interesting. So we've got evidence both in natural settings and from laboratory investigations that basically oil formation doesn't take fast periods of time. Like you say, sort of time is not the hero of the plot here. It's high temperatures, presence of water, perhaps conditions of burial, but those are kind of the important factors that we're talking about. Yeah. So that's interesting because so often you kind of hear people just make these claims that oil formation requires millions of years. And this is a kind of defeater for the creationist position. And it seems from what you're saying that that's just really not the case. And that it's known even within the conventional scientific community that that's not the case.
Yeah, I mean, people that study petroleum geochemistry would know this, but people that haven't studied it, they might still be geologists, but if they haven't studied it, they may not be aware of it.
Yeah. That's very interesting. So moving on then from sort of the formation of oil, what happens to oil once it's been generated? When we go looking for oil, when exploration geologists are looking for oil, are they finding oil in the place where the oil formed, or has something else happened to it subsequently?
The oil migrates because oil compared to water is buoyant, so it tends to go up towards the surface. There's three main kinds of migration. There's primary migration and there's secondary. Primary is when it gets expelled out of the actual source rock itself. Incidentally, back to the laboratory studies, I'll use some big words here. Laboratory hydrosporolysis. Hydrosporolysis really means cooking it up in the presence of water. That provides evidence for simultaneous oil generation and expulsion from source rocks. Upon heating, decayed organic matter decomposes to an expanding tarry bitumen. The expansion causes the rock bedding plane to fracture. This allows liquid oil to be expelled. So it's all happening together. Now, secondary migration refers to the oil going from the source rock to the reservoir rock. The expulsion or primary migration, the transport, the secondary migration often happens together. So where does it accumulate? So it tends to migrate upwards because of that buoyancy. So it accumulates in a porous rock called a reservoir. Incidentally, it's probably a popular conception that oil is in big caverns in the ground, but that would be extremely rare. It's actually like if you picture down the beach and the sand in the beach and you pour water, it sinks in because it goes in between the sand grains. So a reservoir rock is porous like that, and the oil is in those pores, and that may be a sandstone or a limestone. But so it goes up into a reservoir rock, but in order to be trapped there, it needs a seal. So it needs a rock overlying that is not porous and permeable. It's actually impermeable, so it stops migration going further. That can be a rock like a shale. That can be a cap rock.
Yeah, so I'm trying to visualize this. So you've got a source rock where the organic material was kind of buried. It was buried in a sediment. That's the source rock. That's where the kind of breakdown of the organic material happens. But as it breaks down, you're saying it actually expands and in effect fractures the source rock, so it escapes. And because it's buoyant, it kind of escapes from the source rock generally upwards.
Yeah.
Until it meets some kind of, well, it accumulates in this permeable reservoir rock, but it accumulates there because it's met a barrier. So you might have some kind of barrier where it can't travel any further. Is that kind of the picture that I'm getting here?
Yeah, that's correct. Yep.
Yeah. What kind of trap? We call these oil traps, don't we? What kind of traps are there? Because I think there are different types. Is that right?
Yeah, there's three main types there. There's structural traps, there's stratigraphic traps, and a combination of the two. Now, structural traps are formed by folding or faulting. You know, like that might be what's called an anticline. So the oil comes up and hits an impermeable barrier. It's trapped in the anticline. Another kind can be like a fault that can be trapped with some impermeable rock on the fault plane. Now, stratigraphic traps, these are a lot harder to find. I mean, early exploration, companies tend to go for the bumps, you know, the anticlines. You know, they're easier to recognise on seismic sections. You know, you know, their structures are easier to recognise. The stratigraphic traps can be a lot trickier. They can be formed due to changes in the rock type or reservoir quality. For example, a reservoir might pinch out. You know, this permeable reservoir may pinch out, or there can be an unconformity. It can migrate up and then hit an unconformity where the rock above the unconformity is impermeable. So, and then, as I mentioned, there's combinations where you can have the faulted anticline, or you can have stratigraphic traps that are fault. There's various combinations.
Yeah. I suppose with those structural traps, in effect, so if you've got a fault plane, for example, it might bring impermeable rocks up against permeable rocks. So that's going to kind of trap the oil there in the permeable rock.
Oh yeah. Conversely, if on the fault plane, if the fault plane is not, if it is permeable, then the oil might escape too. So
yeah,
you really need a good combination of a reservoir rock with a impermeable rock against it to trap it. You know, if it's permeable on both sides of the fault, then it's just going to escape.
Yeah, that's very interesting. Now, we've talked about this oil migration, this concept of primary migration out of the source rocks and then secondary migration into the reservoir rocks. What kind of timescales are we talking about? How long does it take? How far does the oil travel, for one thing? And how long does it take to get into the reservoir? Is that something that might take long periods of time?
No. The rate of secondary migration is being modelled. I found an article in the American Association of Petroleum Geologists Bulletin, and they modelled it, the migration at approximately 1 kilometre per year.
Wow. So 1 kilometre a year is...
So obviously you don't need millions of years, you know. So for those who believe in a deep time framework, this would seem nearly instantaneous, you know.
Wow, that's much higher than I thought you were going to tell me. So 1 kilometre a year, that's remarkably rapid.
So
yeah.
Let me.
Well, that's blown my mind.
That doesn't seem very rapid. That doesn't seem very rapid to me. Tell me about how far they're going. That's what I need to know here. Because 1 kilometer a year, I can manage that. That's pretty easy. But how far is the distance we're moving?
Good
Well, it can be
question.
many kilometers. It can be, it depends on the particular situation in which basin and how it's all structured. But as I understand, it could even up to 100 kilometers. You know, it can be
Okay.
quite radical.
Okay.
Probably a lot less than that in most cases, though.
Mhm.
But there are some very big fields in the Middle East that may have had long distance migration.
So the migration then you're
Yeah.
talking about on the order of decades, maybe a century for a big migration.
No, I mean it's really like even like with groundwater, water fluids can flow in porous media quite easily, you know.
Mm.
So
Yeah. Wow. Yeah, that's very interesting. So we're talking about I'm kind of thinking about this as we go along. So the formation of oil itself is highly dependent on temperature. Doesn't require long periods of time. In fact, we've got places where oil generation today is almost instantaneous. We've got primary migration that's kind of happening as the oil is generated. Secondary migration, where even if it travels reasonably long distances, it's the kind of thing that you can envisage happening within, maybe 100 years or so. This is all, I mean, geologically speaking, this is all remarkably rapid. This is really sort of rapid processes that we're talking about here. Richard, could you sum up for us? We haven't really sort of talked about a kind of a creationist model for understanding oil formation. So just kind of summarize for us, in a creationist framework, when is this oil being formed? What are the processes involved that are, lead into the burial of this organic matter? When is this sort of migration and accumulation happening? So give us an overall sort of creationist picture, if you like.
well, a key thing is tectonic activity. So in the flood, there would have been huge upheavals. You know, there'd be subsidence, there would have been uplift, and then the time of seafloor spreading, also enormous tectonic activity, and with collisions of continents, and you get all sorts of structures formed. You get heat involved with all this tectonism too. So it's quite easy to fit it into a young Earth creation sort of scenario. I've written detailed information about different times during the geologic column, how things would have formed. But so the generation and migration of petroleum can occur rapidly, especially under increased temperatures. We've covered that. And there's so much. There's the catastrophic nature of the stratigraphic record itself. That applies to sediments such as source rock, reservoir seal, and overbed. There was an anti-creationist, Professor Derek Ager of the UK. He said the rock record is like a soldier's tour of duty, long periods of boredom punctuated by brief periods of terror. In other words, the rocks form really fast, but then he had the faith of millions of years where there was long periods in between. So,
Yeah.
I mean, catastrophism has sort of come more in vogue, but they still have the framework of millions of years, you know.
I guess
But even
sorry, go ahead.
yeah, but even with millions of years, you get crazy results, because I saw some in West Java, you know, where Jakarta, the capital of Indonesia, it's sinking about 6 centimeters a year. Now, there's been some modelling of sediments getting buried over 40 million years. Well, 40 million years, you'd end up in the mantle. Jakarta would end up in the mantle, So it doesn't work, It can't be, at a constant rate for millions of years.
Yeah. Yeah. I guess in a kind of creationist framework, if we're thinking about this worldwide flood where massive sedimentary deposits are being laid down, burying vast quantities of organic matter, and elevated temperatures presumably being generated quite quickly, you've got great conditions for the breakdown of this organic matter into the sort of raw materials that are going to produce the oil into this kerogen. So really the flood and its aftermath just gives us ideal conditions to produce these big deposits of oil. And then the timescales, like you say, if you've got the tectonics, you've got sort of folds and anticlines and faults and things being generated, you're producing the traps that then that oil can be accumulated within. So the timescales don't have to be very great. We can sort of easily see how that might have happened within the young Earth framework. I want to come on to another question, because the formation of oil is one thing and the accumulation of oil. But I've often heard critics say about young Earth geologists that we couldn't find oil. We wouldn't be successful in locating oil. And I think the argument seems to be that most geologists working within the oil exploration industry accept the long-age uniformitarian model of Earth history. And they are successful in finding oil deposits. And so this seemingly validates their long-age uniformitarian model. What would you say about that? Does successful oil exploration really validate uniformitarianism?
Well, there's two things. One, uniformitarian, there's lots of things that happen in geology that may be once-off, I mean, if Noah's flood is once-off. But in terms of the time, big time, that's, I've never seen, well, it's really the real key thing is the relative order of events, because people, explorationists, they have these charts where they have, this is when the source rock cooks up, this is when it generates, this is when its trap is formed, this is, they have these sort of charts. So it's the relative order of events, that is important. It's not the absolute time scale at all. It's not necessary. I mean, all these things can happen really fast. It's just the relative order, the sequence of events. That's the key.
Yeah. So that's interesting, because obviously within the creationist model, that relative order of events is basically the same. So what we're looking for, in effect, I suppose, is a particular, what would you say, subsurface geometry where oil might be formed and then accumulated. Is that what you're looking for? You're looking for anticlines, these sort of folds. You're looking for faults where, so that's a matter of kind of observational science. It's not very sort of origins driven, is it? Ideologically driven, I guess.
I mean, what you really need is, to start with, is a source rock. If you don't have a source rock, you don't have any petroleum. So
right.
So once they've found a source rock, they may have found it with outcrops or with some drilling. The next step would be to to do geophysics, like particularly seismic surveys, to get an idea of the configuration of the traps.
Mm.
And then comes the drilling. And jokingly, the drilling is called the rotary lie detector. In other words, you're drilling down and you either find something or you don't. There's a lot of, despite all the science that goes in, there's still luck. Like in Western Australia, a company was, but they knew another company had found in a sandstone, they'd found gas. So this company looked for, they saw that as an analog, and so they had this target. They drilled it, and so instead of finding natural gas in a sandstone, they found oil, which is a lot more valuable, in a fractured dolomite. So you get these surprises. And then conversely, a company was looking for oil in the dolomite and they found gas, So, sometimes there's interesting surprises, but that's what I love about exploration. There's always the unexpected, or there's something new comes along. It's fascinating stuff.
Yeah. You mentioned seismic profiling there. Just explain that for our listeners. What is seismic profiling and how is it used in exploration geology?
Well, it's a bit like echo sounding. It's basically it can be it's a means of like sending like a sound signal into the ground, and it bounces off of different layers, and that you can get a picture of what the structure is in underground. I mean, offshore they have boats that pull all these streamers behind, and they set off air guns, and that air gun signal goes through the seabed into the rock and bounces back up, and they've got hydrophones which will pick up the signal. And then on land, the favourite technique these days seems to be vibrasize, where they have a truck and it puts down a pad and it vibrates the ground. And once again, it sends a signal into the earth. It bounces off of different layers, and they get the signal back and they get an idea. They do a lot of fancy processing, you have to be a pretty good mathematician, I think. Anyway, so it gets all processed and then interpreted,
Mm-hmm. And what other kind of geophysical techniques are used in exploration?
Well, there are some techniques like gravity and magnetics, other things that give an idea of structure. Gravity picks up, rocks that may be more dense or less dense. Magnetics may pick up, give an idea of the depth of the basement. The basement rocks, the crystalline basement rocks may be more magnetic than the sediments overlying. I was on a funny job where a junior company, they thought they had a nice booming reflector on the seismic, but they failed to detect the magnetics. And when we got into the target zone, all this flake rock started coming up, these chips, and there were 3 other geologists on site, and I said, "Oh, this could be basalt, because if it's basalt, it's got magnetite." So I pick bits of it up with a magnet. They still didn't believe me. And then about a year later, I got a letter from that company about something else. P.S. You were right. The petrography indicated it was a basalt. So instead of drilling a nice reservoir, they drilled a basalt. So, especially in frontier areas that aren't very well explored, it pays to try all sorts of different methods, really.
Mm-hmm. So, is there anything, inherently evolutionary about any of these exploration techniques? If you're a creationist and you're interested in geophysics and you want to kind of go into industry and work for an oil exploration company, are you going to, is this going to be a problem because you're having to accept these evolutionary techniques? It doesn't sound like
really.
it to me, but
No, I mean, some of the early modelling may have had not the best assumptions, like, for example, not take some. They may have got some big numbers when they were doing crunching numbers, when they assumed that there was the heat flow was conduction, which is a lot slower than convection and advection. They also may not have considered the movement of hot water. So there's a number of things in the early models which really weren't realistic, to the real world. So once again, it's the relative order of events that is key. Like there may be a critical point that is necessary to have an accumulation where you got your source generating, migrating, trapping, and not breached, with later tectonism. So, it's the order of events. It's the critical thing.
that's very helpful. Todd, have you got any other questions for Richard about any of this as a non-geologist?
Yeah, I do. I've been listening. Wait a second. Yeah, I do. I've been listening with great interest here, and the thing that I keep wondering about, and this is going to be marginally related to this, but if we can make petroleum, why don't we? What is the what's the economic balance here? And I suspect the economics must be the heat source of how to heat things up, but I'm wondering if you've got some insight on that. Why don't we make petroleum? Why are we drilling for it?
It has been made. Algae has been cooked up to form oil, but it's not economic. It's we've already got billions of barrels of oil in the ground. They may produce algae in a local little plant, but it's not going to produce billions of barrels, which are already there in the ground. So it's all a matter of economics. So it's proven that you can make oil. You can use like this with coal that can produce methane too. In fact, coal bed methane is an industry in itself, but that's natural, in the ground.
Okay.
The conference that I was invited to was the International Conference on Coal Seam Gas and Oil. So there were people from all over the world. It was so it happens naturally, getting methane from coal.
Right.
In fact, in coal mines, it can be very dangerous, the methane. There's explosions and people get killed. So to answer your question, yeah, we can make oil and gas, but it's just not economic.
Right. Yeah.
I guess you have to put more energy in than you get out, I suppose. Yeah.
Yeah, I guess so.
Yeah. And the scale of having that much algae. I mean,
yeah.
I mean, I've known a couple of guys in my life who were trying to do biodiesel with their cars and going around to McDonald's and getting old cooking oil and trying to convert it to a biodiesel by a esterification process. But that was a lot of effort for maybe a tank of diesel. And I thought, this isn't very... It's possible to make these things in laboratory situations, but it's just not... It just doesn't scale to the kind of need that we have, I guess, is basically the problem.
Yeah.
Okay.
Yeah.
Exactly.
Yeah. Yeah, very good. That's been very interesting. I hope our viewers have found that helpful, because this whole issue of oil formation is one that I, over the years, have encountered time and time again, where people have very confidently told me that oil formation requires long periods of time, and you can't do it in a short time frame. And if you're a young age geologist, you couldn't find oil because it all depends on applying evolutionary techniques. And from what you said, I mean, this is very interesting to me. Here you are, you've had a long career, most of it in oil exploration, and you're telling me that these are not really valid criticisms of the young age model. Oil exploration is a matter of sort of fairly pragmatic exploration. You know, you're looking for a particular order of events, a particular underground geometry, where you're going to find oil, and an oil formation can be really, really very rapid. So that's all incredibly interesting to me. If some of our viewers and listeners would like to find out more about this topic, where could they go? I know that you've written many papers in the creation literature.
In the show notes, yeah.
I mean, there's some stuff that's very technical, so it's a matter of, and if you Google and you find some sort of layman stuff, it'll say deep time anyway. But I mean, like some of the articles that Harry Dickens has written, you know, but, I feel like Clark Kent to Superman, you know.
Right.
Richard
Clark
Bruce to
Kent.
Harry Dickens. Anyway, well, in those articles, I've tried to sort of summarize a lot of the concepts anyway. Probably a key one is on what's called petroleum systems. So that goes right through to source migration, reservoir, seal, all that sort of stuff. So that paper alone on petroleum systems was in the Journal of Creation. That one alone would give you a good overview.
Yeah. Well, we'll make sure to link to all of that in the show notes. Todd, any last thoughts, comments before we sort of round out this episode?
Just one stupid comment. The meme that's going around talking about dinosaurs turning into petroleum, and then we use it to make plastic dinosaurs. You're telling me that's not accurate. Is that right? This is algae that makes petroleum, not dinosaurs, right?
That's correct. Yeah, yeah.
All right. Well, it's good to have that cleared up because I see it all the time.
I mean, they're at the top of the food chain, you know, so, you know, there's a lot more algae than there is dinosaurs, you know.
Yeah, that's right. That's right. That's right.
Yeah. Well, trust Todd to kind of get to the heart of the whole issue.
There you go.
Yeah, that's great. Plastic dinosaurs. Yeah. Yeah, brilliant. Well, thanks so much, Richard, for coming on. We've wanted to have you on for a while, and so we're so glad that you were able to make time to be here today and talk to us about oil formation and generation exploration. That's it, I think, for this week. I hope you've enjoyed that. We're going to be back in a fortnight's time with another interesting topic, and we hope that you'll join us then. So we'll see you in a couple of weeks. We'll see you then.
Thanks for listening to this episode of Let's Talk Creation. For more information, visit us at letstalkcreation.org, where you'll find an archive of past episodes and all our show notes. If you'd like to leave a comment or make a suggestion, you can find us on all the major social media platforms. Let's Talk Creation is brought to you in the U.S. by Core Academy of Science and in the U.K. by Biblical Creation Trust. As a listener-supported ministry, we are grateful for all of your financial support. Find out how you can make a contribution at our website, letstalkcreation.org. Also remember to like, subscribe, and share this episode with your friends. Thanks, and see you next time.